What if everything you think you know about time is wrong? We're used to thinking of time as a straight line, past, present, future, ticking away like clockwork. But what if time isn't just a single dimension? What if it's more like a vast, twisting labyrinth with hidden layers and secret passageways we can't even perceive? This isn't science fiction. Some of the most brilliant minds in physics believe our universe might be hiding extra dimensions of time, dimensions that could rewrite the rules of reality itself. Imagine standing in a room with invisible doors all around you. You can't see them, but they're there, waiting to be discovered. That's what these hidden dimensions of time might be like, uncharted territories of existence just beyond our senses. Some theories suggest these extra dimensions could explain mysteries like déjà vu, or how particles seem to communicate faster than light. Others propose they might even hold the key to time travel. But here's the thing, if these dimensions exist, why can't we see them? And if we could, what would that mean for our understanding of life, the universe, and everything in it? Today, we're going to unravel 30 of the most fascinating theories about these hidden dimensions of time. From cutting-edge physics to mind-bending speculation, we'll explore ideas that stretch the limits of imagination. Some will sound like pure magic, others might leave you questioning the very fabric of reality. But one thing's for sure, by the end of this journey, you'll never look at time the same way again. So buckle up, we're about to dive deep into the unseen layers of existence, where the ordinary rules don't apply, and every answer leads to a dozen new questions. The first stop on our journey takes us into one of the most mind-bending ideas about time, the block universe theory. Picture reality not as a flowing river, but as an enormous, unchanging sculpture. Every moment, your first memory, the words you're hearing right now, events centuries from now, all exist simultaneously, frozen in place like frames in a film strip. According to this view, time doesn't pass at all. Instead, what we experience as the present is just our consciousness moving through this eternal structure, giving us the illusion of change. Einstein's theory of relativity laid the groundwork for this idea. He showed that time isn't universal, it bends and stretches depending on motion and gravity. There's no single now that applies everywhere. What's the present for you might already be the past for someone moving at high speed or near a black hole. This shatters our everyday sense of time, suggesting the past, present, and future aren't just connected, they're equally real, forever locked in place. Think of it like reading a novel. The entire story exists from the first page to the last, but you only experience it one word at a time. The block universe argues reality works the same way. Your life is already written, and you're just flipping through the pages. Some physicists take this further, proposing that free will might be an illusion, since every choice you'll ever make is already part of the block. But here's where it gets stranger. If the future is just as fixed as the past, could there be layers of time we're not perceiving? Dimensions where those pages aren't lined up in a straight sequence? That's a mystery we'll keep unraveling as we explore even wilder theories ahead. But what if the block universe isn't completely frozen? Some physicists argue reality might be more like a sculpture still being carved, where the past and present exist as solid, unchanging layers, but the future remains blank, waiting to be written. This is the growing block theory, a fascinating twist on eternalism that suggests time isn't just a static block. It's a structure that expands as new moments come into existence. Think of it like building a brick wall. Each brick represents a moment in time, cemented into place as it happens. The wall grows taller with every second, but the space above it. That's the unwritten future, still open to possibility. Unlike the classic block universe where everything is predetermined, the growing block leaves room for genuine uncertainty. Your choices matter because the future isn't set in stone. It's being built brick by brick with every decision you make. This idea sparks heated debates. Philosophers argue it preserves our sense of free will better than eternalism, since the future isn't already out there somewhere. But critics point out a paradox. If the past and present are real, fixed entities, why doesn't the future deserve the same status? Some scientists suggest quantum mechanics might hold clues where particles exist in clouds of probability until observed, almost as if reality hesitates before adding the next brick to the wall. The biggest question, though, is whether time itself has layers we can't perceive. Could there be dimensions where the growing block behaves differently, where futures branch like tangled vines? Or perhaps realms where time doesn't grow forward at all, but in directions we can't even fathom. As we peel back these theories, one thing becomes clear: time is far stranger than we ever imagined. Now consider this: what if time isn't a single arrow but a pair of them, crossing paths in ways we barely understand? This is the radical premise of two-time theory, which suggests our universe operates not with one dimension of time but two. At first glance, it sounds impossible. How could we experience multiple timelines simultaneously? Yet some physicists argue this very idea might solve mysteries that have baffled science for decades. Take quantum mechanics, where particles exist in ghostly superpositions until observed. In a world with two temporal dimensions, these quantum oddities might make perfect sense. Imagine time as a grid instead of a line. A particle's strange behavior existing in multiple states at once could simply be its movement across this hidden temporal landscape, unseen by our one-dimensional perception. It's like trying to describe a three-dimensional object using only a flat photograph. You're missing entire layers of complexity. Then there's the arrow of time. Why does entropy always increase, creating an irreversible flow from past to future? Two-time theory offers a stunning possibility. Entropy might be the shadow cast by our limited view of time's full structure. Think of a river splitting around a rock. From above, you'd see both branches, but standing in one, you'd only experience a single current. Similarly, our perception of time's one-way flow could be an illusion created by our position in a vaster temporal geometry. Could this mean alternate versions of reality are unfolding in directions we can't access? Some models suggest these extra time dimensions might allow for closed time-like curves, loops where cause and effect twist back on themselves. That could explain phenomena like déjà vu, where fragments of unseen timelines momentarily brush against our own. Russian physicist Igor Bars even proposed that two-time physics might unify all fundamental forces, weaving gravity and quantum mechanics into a single mathematical tapestry. Yet if extra time dimensions exist, why don't we notice them? One compelling answer comes from string theory, where dimensions beyond the familiar four may be compactified, curled into spaces so tiny they're invisible to us. Picture an ant walking along a telephone wire. From a distance, the wire looks one-dimensional, but up close, the ant can circle its surface, exploring a hidden second dimension. Our relationship to deeper layers of time might be just as subtle, hidden in plain sight. The implications are staggering. If time has multiple dimensions, our entire concept of reality becomes a narrow slice of something far richer, like Flatlanders discovering the third dimension. Perhaps consciousness itself is bound by our single time perspective, leaving whole realms of experience beyond our grasp. As we peel back these layers, one truth emerges: the universe is far stranger, far more intricate than our senses will ever reveal. What if every choice you've ever made, big or small, didn't just lead you down one path but splintered into countless others? This is the heart of the higher dimensional fabric theory, where time isn't a single thread but an intricate weave of parallel realities, each one a ripple from every possible decision. Imagine time as an enormous, shimmering tapestry, with every thread representing a different version of existence. Some threads run parallel, never touching. Others twist and knot, creating intersections where realities briefly brush against each other. This idea isn't just speculative fiction, it's rooted in the mathematics of multiverse theories. Take quantum mechanics, where particles exist in multiple states until observed. Some interpretations suggest that every quantum possibility spawns a new universe, meaning there's a reality where you took that job offer, a reality where you never existed, even a reality where dinosaurs evolved intelligence. These branching timelines aren't separate, they're layered like sheets in the higher dimensional fabric, vibrating against one another in ways we can't perceive. Think of it like a book with infinite alternate endings, all written simultaneously on translucent pages stacked together. When you flip through it, you only see one ending at a time, your current reality, but the others are still there, hidden in the gaps. This could explain eerie phenomena like the Mandela effect, where large groups remember events differently. Could those be echoes bleeding through from adjacent layers of the fabric? String theory takes this further, suggesting that what we experience as time might just be one dimension in a far richer structure. Just as a two-dimensional creature can't comprehend depth, we might be blind to the full geometry of time's weave. Some models propose that gravity, the weakest force in our universe, leaks into our reality from these hidden layers, tugging at the edges of our perception. The implications are staggering. If time is a higher dimensional fabric, then now is just the slice we're tuned into. Death, birth, even consciousness might be local phenomena, confined to our single thread, while other versions of us live out different stories elsewhere in the weave. It's a humbling thought. The universe might not just be stranger than we imagine, but stranger than we can imagine, with time itself as the ultimate unfinished masterpiece. Now let's peel back another layer of time's mystery, one that turns our understanding of reality inside out. The holographic principle suggests something astonishing. Our three-dimensional universe, with all its depth and complexity, might actually be a projection from a two-dimensional surface at its boundaries. It's as if everything we experience, every star, every thought, every passing second, is just a shadow cast by information etched onto some cosmic film. But here's where it gets stranger. If space itself is an illusion, what does that mean for time? Think of a movie projected onto a screen. The images appear three-dimensional, full of movement and life, but they're all encoded in flat, static frames. The holographic universe works similarly. Our flowing, changing reality could be the projection of timeless data stored on a distant horizon. Time, in this view, might not be a fundamental feature of the cosmos. Instead, it could emerge from the way information interacts across dimensions, like the illusion of motion created by flipping through a flipbook. This idea isn't just wild speculation. It comes from black hole physics, where the information swallowed by a singularity isn't lost but smeared across its event horizon like ink on parchment. If black holes can encode three-dimensional events in two dimensions, why not the entire universe? Some physicists argue that time itself could be a side effect, a byproduct of how this underlying data organizes itself. Imagine standing in front of a mirror. Your reflection moves when you do, but the glass itself doesn't change. The holographic principle hints that time might be like that reflection, an emergent dance, while the true mirror of reality remains timeless. This could explain why quantum particles seem to know things instantaneously across vast distances. If their states are determined by deeper, non-local information, time as we know it might just be the surface ripple of something far more alien. The implications are dizzying. If time isn't fundamental, then cause and effect, aging, even history itself might be secondary phenomena, stories we tell ourselves to make sense of a reality that operates on entirely different rules. Could this be why time feels so fluid in dreams, or why near-death experiences often describe moments stretching into eternities? When we peer into the holographic depths, we're left with a haunting question. If time is just an echo, what's really doing the singing? Let's untangle one of the strangest ideas in physics: time loops, not as science fiction, but as real mathematical possibilities hidden in Einstein's equations. Closed time-like curves, or CTCs, are pathways through spacetime that circle back on themselves, allowing an object, or even a person, to return to their own past. Picture walking in a straight line, only to realize you've somehow ended up where you started, not just in space but in time. General relativity makes this eerie scenario plausible. Warped by extreme gravity, like near a spinning black hole, spacetime could twist so severely that time itself bends into a loop. The equations don't forbid it. In fact, famed mathematician Kurt Gödel proved it's theoretically possible in a rotating universe. But here's the catch: if you could meet your younger self, what stops you from altering events so drastically that you'd never exist? This is the infamous grandfather paradox. Kill your ancestor, and you erase your own existence, making the murder impossible in the first place. Physicists have proposed wild solutions to this conundrum. One answer comes from quantum mechanics, the idea of self-consistent timelines. Every action you take in the past would already be part of history, forcing events to unfold in a way that avoids contradictions. Think of it like a snake swallowing its own tail. Your future actions in the past were always destined to happen, locked in an unbreakable loop. Another twist: parallel universes. Each trip through a time loop might spawn a new reality, branching off like a split in a river. You couldn't change your past, but you could create a new timeline where different choices play out. Some theories even suggest CTCs might explain déjà vu, fleeting glimpses of loops we've already traveled, echoes of time folding back on itself. The most mind-bending proposal comes from physicist Igor Novikov, who argued that the laws of physics might conspire to prevent paradoxes entirely. Try to shoot your grandfather, the gun jams, a bird distracts you. The universe becomes a cosmic editor, snipping out logical inconsistencies to preserve causality. It's as if reality has built-in safeguards, ensuring time loops don't tear the fabric of existence apart. Yet if closed time-like curves exist, why haven't we met time travelers? Perhaps because these loops are vanishingly rare, hidden in the gravitational whirlpools of cosmic extremes. Or maybe, just maybe, we're already part of loops too vast to notice, our lives threading through time's hidden spirals without us ever realizing it. Here's something that sounds impossible: a structure that moves without ever slowing down, not because it's defying physics, but because it exists in a state of perpetual motion built into the very fabric of reality. This isn't science fiction. It's the bizarre world of time crystals, a discovery so strange that even Nobel laureates initially doubted it could exist. Unlike ordinary crystals like diamonds or snowflakes, which have atoms arranged in repeating spatial patterns, time crystals repeat in time. Their atoms oscillate in a never-ending cycle, locking into a rhythm that persists without energy input, like a clock that ticks forever without winding. The idea was first proposed in 2012 by physicist Frank Wilczek, who wondered if temporal symmetry could be broken the way spatial symmetry is in regular crystals. At first, the concept seemed to violate fundamental laws. How could something cycle endlessly without losing energy? But by 2017, two separate teams had created time crystals in labs using chains of ytterbium ions and diamond impurities. These systems didn't achieve perpetual motion in the classic sense. Instead, they tapped into quantum weirdness to stabilize their oscillations. Think of a pendulum that swings left and right not because you pushed it, but because the universe demands it keeps swinging in that exact pattern. What makes time crystals revolutionary isn't just their defiance of equilibrium, it's what they reveal about time itself. In everyday life, time feels uniform and featureless, like an empty highway. But time crystals suggest moments could have hidden structures, like mile markers woven into reality's fabric. Some physicists speculate these structures might hint at deeper layers of time, dimensions where causality operates differently. Imagine a river with whirlpools. The water keeps flowing forward, but within those spirals, time might loop or fold in ways we can't perceive. The practical implications are staggering. Time crystals could lead to unhackable quantum computers, their oscillations acting as perfect clocks for error-resistant calculations. Others theorize they might help probe the boundary between quantum and classical physics, revealing how time emerges from the microscopic realm. But the most tantalizing idea: if time can crystallize, what else might it do? Could there be temporal superconductors where cause and effect flow without resistance? Or dimensions where time crystallizes into architectures we can't even fathom? One thing's certain: the discovery of time crystals has cracked open a door to a world where time isn't just a backdrop, but an active, dynamic player in the universe's grand design. What if the Big Bang wasn't the beginning, but the middle? That's the spine-tingling premise of the Janus point theory, which flips our understanding of cosmic history upside down. Picture the birth of our universe not as a single explosive moment, but as a symmetrical divide, like a droplet of water splitting in midair. On one side, time flows forward as we know it, with entropy increasing and galaxies racing apart. On the other, a mirror universe unfolds where time runs backward, with stars assembling from scattered light and broken teacups leaping back onto tables. This idea stems from a radical reinterpretation of the laws of thermodynamics. Normally, entropy, the measure of disorder, always increases, giving time its irreversible arrow. But physicist Julian Barber argues that at the Big Bang, entropy didn't start at zero. It hit a minimum, like the still point at the center of a pendulum swing. From that Janus point, named after the two-faced Roman god, time could have branched in opposite directions, creating twin universes with reversed thermodynamic destinies. Imagine standing at the edge of a vast hourglass. The sand above represents our universe, grains falling into the future. Below, an inverted hourglass scatters sand upward, the mirror cosmos where cause and effect work in reverse. In that universe, beings would perceive our past as their future, watching as shattered glass shards reassemble into cups or light converges into stars. To them, we'd seem impossibly backward, living in a world where entropy defies their natural order. The implications are staggering. If true, the Janus point theory could explain why the Big Bang appears so finely tuned. It wasn't a beginning at all, but a balancing act between two cosmic timelines. Quantum fluctuations in the early universe might not be random, but echoes from the mirror side, whispering through the singularity. Some models even suggest dark matter could be the gravitational shadow of our twin universe, tugging at galaxies from across the temporal divide. But here's the haunting question: if time flows both ways, could the mirror universe harbor mirror versions of us? Not exact copies, but beings shaped by the same quantum symmetries, their lives rewinding as ours advance. Some physicists speculate that consciousness itself might be entropy-dependent, meaning our mirror twins could experience reality in ways utterly alien to us, thinking backward, remembering the future. The Janus point theory remains contentious. Critics argue it's untestable, a beautiful metaphor without empirical teeth. Yet it challenges our deepest assumptions about time's arrow, suggesting the universe might not have a direction, just a pivot point with two eternities stretching outward like wings. Whether or not the math holds, one thing's certain: the Big Bang may have been far stranger than we ever dreamed, a moment not of creation but of cosmic symmetry, splitting time itself in two. We take it for granted that time flows in one direction, eggs crack but never uncrack, ice melts but never refreezes spontaneously. This relentless march toward disorder is called entropy, and it's the reason we remember the past but not the future. But here's the puzzle: the fundamental laws of physics don't care about time's arrow. Run them backward and they work just fine, so why does entropy only increase? Could hidden dimensions of time hold the answer? To grasp this mystery, think of a deck of cards, shuffle it, and the order dissolves into chaos. That's entropy at work. But in theory, there's nothing stopping the cards from randomly reshuffling into perfect order. It's astronomically unlikely but possible, yet we never see it happen. The universe seems hardwired to favor disorder, as if time itself has a one-way sign. Some physicists argue this asymmetry isn't just chance, it's a clue that our perception of time is incomplete, like seeing only the crests of ocean waves while missing the troughs beneath. Enter the hidden dimensions hypothesis. Imagine time isn't a single line but a branching structure, with alternate temporal paths invisible to us. In this view, entropy might increase because we're trapped on a one-way thread of the larger tapestry. Other dimensions could harbor timelines where entropy decreases, flowing backward like rivers against the current. Our universe's arrow of time would then be a local quirk, not a universal rule. This idea finds eerie support in quantum mechanics, where particles occasionally behave as if they're influenced by futures that haven't happened yet, almost as if they're glimpsing those hidden temporal branches. The wildest twist, some models suggest the Big Bang wasn't just the start of our universe, but a collision point between forward and backward flowing timelines. Picture two mirrors facing each other with the Big Bang as the point where they touch. On one side, time expands into the future we know. On the other, it unfolds in reverse, a mirror cosmos where shattered glass leaps back into windows and scattered light reconverges into stars. If true, our experience of time might be just one half of a vast, symmetrical dance with entropy's arrow pointing the way simply because we're on this side of the mirror. Yet if hidden temporal dimensions exist, why don't we detect them? One possibility lies in the geometry of space-time. Just as a sheet of paper appears flat until you fold it, extra time dimensions might be curled up at scales so tiny they evade our notice. But their influence could ripple through reality in subtle ways, nudging entropy toward disorder like an unseen hand tilting the cosmic scale. Others propose that consciousness itself is bound to the forward flow of time, filtering out dimensions where cause and effect run backward. The implications are profound. If entropy's arrow is shaped by unseen temporal layers, then free will might not be an illusion. It could be the result of branching possibilities in higher dimensional time. Even death could take on new meaning, not as an end, but as a transition to dimensions where time's flow is unrecognizable. This isn't just theoretical gymnastics, it's a radical rethinking of reality's scaffolding, where the one-way street of time becomes a sprawling intersection of alternate temporal highways. So the next time you watch steam rise from your coffee, remember, the universe's obsession with disorder might be hiding a secret, a whisper from the dimensions of time we've yet to discover. What if the ultimate theory of reality contains no time at all? That's the startling implication of the Wheeler-DeWitt equation, a foundational formula in quantum gravity that mathematically erases time from the universe's blueprint. Developed in the 1960s by physicists John Wheeler and Bryce DeWitt, this equation attempts to unite Einstein's general relativity with quantum mechanics, but in doing so, it paints a picture of reality where time might not exist at the deepest level. At first glance, the equation looks deceptively simple, like a stripped-down version of Schrödinger's famous wave equation. But there's one glaring omission: the time variable. Gone, vanished. In its place stands a frozen mathematical landscape where nothing changes, nothing evolves, just pure static geometry. It's as if the universe hit pause at the quantum level, leaving us with a cosmic snapshot instead of a movie. This bizarre feature sparked heated debates. Is time truly fundamental, or is it something that emerges from deeper, timeless physics, like temperature emerging from the chaos of molecules? Proponents of timeless physics argue that our experience of time might be an illusion, a side effect of quantum entanglement. Picture 1,000 metronomes ticking randomly in a room. From the noise, your brain picks out rhythms patterns that aren't really there. Similarly, time could be a story we tell ourselves to make sense of underlying quantum correlations. The Wheeler-DeWitt equation suggests that at reality's core, there's only an eternal now, with past and future as perspectives woven by conscious observers. But critics push back. If time isn't fundamental, why does it feel so concrete? Why do clocks measure it so precisely? Some physicists propose that time emerges from quantum subsystems interacting like how the surface of a lake seems smooth until you zoom in and see the ripples. In this view, the Wheeler-DeWitt equation describes the whole lake, while our experience of time comes from studying its waves. Others, like Nobel laureate Roger Penrose, argue the equation is incomplete, missing quantum gravity's true dynamics. The stakes couldn't be higher. If time is emergent, it reshapes everything from black holes to the Big Bang. Singularities might not be cosmic beginnings, but places where time crystallizes out of timeless geometry. Even entropy's arrow could be an echo of deeper symmetries breaking. Yet if time is fundamental, the Wheeler-DeWitt equation may need rewriting, hinting at undiscovered physics. One radical interpretation: the equation describes a multiverse where every possible configuration exists simultaneously, and time is just our path through this vast landscape. Imagine a library containing every book ever written. Your life would be reading one word from each book in sequence, creating the illusion of a story unfolding. The Wheeler-DeWitt equation might be that library's catalog, timeless and complete. Whether time is real or illusory, the Wheeler-DeWitt equation forces us to confront a profound truth. Our most basic intuitions about reality might be shadows on the cave wall, flickering glimpses of a far stranger cosmos. As we peer deeper into quantum gravity's equations, we're left wondering, if time isn't fundamental, what else might be an illusion? And if it is, why does the universe seem so determined to hide it? String theory paints a picture of reality that shatters our everyday notions of space and time. At its core, this framework suggests the universe isn't made of point-like particles, but of tiny, vibrating strings, filaments of energy whose oscillations give rise to everything from electrons to gravity. But here's where it gets surreal. For the math to work, these strings don't just dance through the familiar 3 dimensions of space and 1 of time. They require extra dimensions. Some theories propose as many as 10 or 11, curled up into shapes so small we've never detected them. What if some of these hidden dimensions aren't spatial at all, but temporal? Imagine time not as a single river, but as a braided stream, with currents flowing at different speeds or even in different directions at microscopic scales. In string theory's landscape, what we perceive as a uniform flow of time could be the net effect of multiple temporal dimensions interacting. At the quantum level, particles might experience time in ways that seem impossible to us, like a photon, sampling moments from the future to decide its path in the present, or entangled particles communicating instantaneously because they're linked through higher temporal layers. This idea gains traction when you consider how strangely time behaves near black holes or at the Big Bang, places where gravity warps space-time to its limits. String theory suggests these extreme environments might expose the scaffolding of hidden temporal dimensions, like a low tide revealing the submerged structures of a coral reef. Some models even propose that the extra dimensions aren't static but dynamic, with time itself bifurcating or folding at scales far smaller than atoms. Picture a drop of water splitting into smaller droplets, except here, it's the fabric of time dividing into threads we can't perceive. The implications are staggering. If time has microscopic layers, it could explain why quantum particles seem to defy classical causality. A particle's ability to exist in superposition, being in 2 states at once until observed, might not be randomness but the result of it tunneling through alternate temporal pathways. Similarly, the famous double-slit experiment, where particles act as both waves and particles, could reflect interference patterns not just in space but across hidden time dimensions. String theorists like Itzhak Bars have taken this further with two-time physics, suggesting that adding an extra temporal dimension simplifies equations unifying all fundamental forces. In this view, our single-time perception is like watching a 3D movie through one lens. We're missing half the picture. the extra time dimension might act as a kind of cosmic synchronizer, aligning quantum weirdness with gravity's rules in ways we're only beginning to glimpse. Yet if these temporal layers exist, why don't we notice them? The answer might lie in their scale. Just as a tightrope looks like a line from afar but reveals its thickness up close, extra time dimensions could be compactified, curled into loops a billion trillion times smaller than an atom. At our macroscopic scale, their effects would average out, leaving only subtle traces, like the way the hum of a distant freeway blends into background noise. The most tantalizing possibility, these hidden temporal dimensions might not be entirely silent. Some physicists speculate that certain quantum phenomena, teleportation, tunneling, even consciousness, could be echoes of interactions bleeding through from deeper layers of time. It's as if we've been listening to reality through a single microphone, unaware of the orchestra playing just beyond our senses. String theory's vision of time doesn't just add new dimensions, it suggests our entire experience of past, present, and future might be a shadow cast by something far richer, stranger, and more beautiful than we ever imagined. What if an entire chunk of human history never actually happened? That's the jaw-dropping claim at the heart of the phantom time hypothesis, a theory arguing that roughly 300 years of the past were simply made up. According to this radical idea, the years between 614 and 911 AD never existed. Instead, they were inserted into the historical record by powerful figures manipulating time itself. If true, it would mean Charlemagne's empire, the rise of Islam, even entire dynasties were elaborate fictions. But how could centuries vanish without a trace? And is there any real evidence to support such an extraordinary claim? The theory was first proposed in the 1990s by German historian Herbert Illig, who noticed strange inconsistencies in early medieval records. Calendars didn't quite align. Architectural styles seemed to leap forward without gradual evolution. Even the Gregorian calendar reform in 1582 appeared to correct dates by removing days that may have never existed. Illig argued these weren't mere errors, they were clues to a massive cover-up, possibly orchestrated by Holy Roman Emperor Otto III and Pope Sylvester II. Their motive, to place themselves at the symbolic year 1000, a moment charged with religious and political significance. But let's dissect the evidence. Proponents point to the lack of reliable primary sources from this period, along with carbon dating anomalies for some artifacts. They highlight how Byzantine, Chinese, and Islamic records from the phantom years might have been altered or misinterpreted. One startling example, the absence of a recorded solar eclipse in Europe during this era that should have been visible based on modern astronomical calculations. To believers, this isn't coincidence, it's proof those skies were never actually observed because the years themselves were fabricated. Critics, however, dismantle these claims point by point. Archaeologists point to uninterrupted layers of settlements, tree rings showing annual growth patterns across the missing centuries, and ice core samples from glaciers that align with documented volcanic eruptions. Astronomers note that eclipse predictions can drift over millennia due to subtle changes in Earth's rotation, explaining the missing eclipse without rewriting history. Linguists add that languages like Old English evolved gradually during this period, something nearly impossible to fake across generations. The most damning counterargument comes from outside Europe. If 300 years were invented, how do we account for perfectly synchronized events in China, the Abbasid Caliphate, and the Maya civilization? Their records independently document comets, wars, and rulers that align precisely with the timeline phantom time theorists reject. Coordinating a global conspiracy on this scale would have required unimaginable control over thousands of scribes, scientists, and cultures, a feat even modern powers couldn't achieve. Yet the phantom time hypothesis raises a fascinating question. How much of history is truly set in stone? we rely on fragile chains of manuscripts, oral traditions, and carbon-dated objects to reconstruct the past. Most of us will never personally verify Charlemagne's birth certificate or dig through 9th century soil layers. In that gap between evidence and belief, theories like Illig's find fertile ground not as literal truths, but as provocations about the malleability of time itself. Whether fact or fringe, the idea lingers like a ghost in the archives, whispering that the past might be far less fixed than we assume. Einstein showed us that time isn't a constant, it stretches and compresses like taffy depending on speed and gravity. But what if that distortion isn't just happening within our universe? What if entire alternate realities exist where time flows at radically different speeds? Imagine a cosmic library where every book is a universe, some with pages turning rapidly, others frozen mid-sentence. This is the startling intersection of relativity and multiverse theory, where time dilation isn't just a local effect, it's the signature of parallel worlds bleeding into each other. Consider a pair of twins separated at a black hole's edge. One stays in orbit where gravity slows time to a crawl. The other ventures closer, returning years later to find their sibling has aged decades. Now amplify this effect across dimensions. If our universe is just one bubble in an infinite foam of realities, each with its own gravitational conditions and velocities, time could be running 1 billion times faster in one universe while barely moving in another. In some, civilizations might rise and fall in what we'd perceive as an eye blink. In others, a single thought could span millennia. The math gets eerie when you apply quantum mechanics. Every quantum decision, like an atom decaying or a photon's path, could spawn new universes through the many worlds interpretation. But if time is relative, those branching realities might not just differ in events, but in the very pace of existence. A universe where you turned left instead of right might also be one where seconds crawl like tar, stretching moments we'd consider fleeting into lifetimes. This could explain why quantum particles seem to know outcomes before they're measured. They're not predicting the future, but interacting with timelines where the future arrived at different speeds. String theory adds another layer. If extra dimensions exist, they might host parallel brainworlds, entire universes floating just millimeters away in higher dimensional space, but separated by temporal barriers we can't perceive. Two realities could overlap spatially while experiencing time at wildly different rates, like neighbors living on floors of a building where one floor's clocks tick 1,000 times slower. The implications are dizzying. A civilization in a fast-time dimension might have achieved interstellar travel while our own species was still single-celled. Conversely, universes where time barely moves could harbor frozen echoes of events from our distant past. The most haunting possibility, these temporal variants might occasionally intersect. Gravitational waves from colliding black holes ripple through space-time. Could similar disturbances briefly bridge time-dilated realities? Some physicists speculate that dark matter's elusive nature might hint at this. Particles we can't see could be massive objects moving through parallel timelines, their gravity leaking into our universe while their light stays trapped in another temporal frame. Even déjà vu takes on new meaning, not as a glitch in memory, but as a fleeting sync with a reality where the same event unfolded at half speed or double time. If time dilation threads through the multiverse, it reshapes how we view existence itself. Death might not be an end, but a transition to realities where our consciousness continues in timelines stretched or compressed beyond recognition. The universe next door could be a nanosecond old or older than eternity, separated not by space but by time's elastic fabric. One thing's certain: if this theory holds, reality isn't just stranger than we imagine. It's stranger than we can imagine, with every tick of the clock whispering secrets from dimensions where time dances to entirely different rhythms. Flip a coin and it lands heads or tails. Play the footage in reverse and the motion looks just as natural. The physics of the event is perfectly symmetrical. Now imagine this applies not just to coins, but to the fundamental building blocks of reality. Welcome to the time-symmetric universe theory, where the quantum world operates without a fixed arrow of time, and particles dance freely between past and future as if the distinction were meaningless. At the quantum scale, particles don't follow the same rules as billiard balls. Electrons, photons, and quarks behave in ways that seem to ignore our everyday sense of cause and effect. Take the famous double-slit experiment. A single particle can act as if it passes through two slits simultaneously, interfering with itself like a wave. But here's the twist. The math works just as well whether you run the experiment forward or backward. The equations governing quantum mechanics don't care about time's direction. They're symmetric, like a palindrome in the fabric of reality. This symmetry isn't just mathematical elegance, it's a radical challenge to our understanding of time. In classical physics, entropy ensures time flows one way, yet quantum particles seem to flirt with time's symmetry, as if peeking behind the curtain of causality. Some interpretations suggest that at the quantum level, every particle's path might include not just movement toward the future, but fleeting loops into the past. Picture a river where most water flows downstream, but here and there, eddies swirl backward, creating momentary reversals in the current. The implications are profound. If time symmetry holds at quantum scales, it could mean that reality's most basic processes are fundamentally reversible. A photon emitted by a star might not just travel forward to your eye, it could, in some sense, also be traveling backward from your eye to the star, with both versions intertwined in a single, timeless event. This idea finds support in the Wheeler-Feynman absorber theory, which proposes that every particle's journey includes advanced waves moving backward in time, perfectly cancelling out effects that would otherwise violate causality. Critics argue that quantum decoherence, the process by which quantum weirdness collapses into classical certainty, breaks this symmetry, locking time into its familiar one-way flow. Yet experiments with entangled particles keep blurring the line. When two entangled particles instantly influence each other across vast distances, could they be exploiting hidden time symmetry, communicating through dimensions where past and future are interchangeable? The most mind-bending possibility, if time symmetry is fundamental, then the macroscopic arrow of time, the reason we remember the past but not the future, might be an emergent illusion, like the way a crowd's noise emerges from individual voices. At the deepest level, the universe could be a vast, timeless mosaic, where every event is eternally connected in a web that doesn't distinguish between before and after. Our experience of time's flow would then be a kind of cosmic perspective, like mistaking a single thread for the entire tapestry. This theory doesn't just challenge physics, it redefines existence. If time symmetry holds, then every moment might contain echoes of its own past and future, woven together in ways we're only beginning to glimpse. The quantum realm could be whispering a secret. That time, as we know it, is just one face of a far stranger, more symmetrical reality. What if the past isn't gone and the future isn't waiting? What if every moment that ever was or will be exists right now, spread across time like landmarks on a map? This is the core of the B theory of time, a view that shatters our instinctive sense of time as a flowing river. Instead, it treats time as a dimension no different from space, where the past, present, and future are all equally real, just separated by coordinates. Think of it like a cosmic DVD. The entire movie exists at once, but your consciousness is the laser moving through it, creating the illusion of motion. This stands in stark contrast to the theory, which insists time truly passes, that the present is somehow special, and the future is unwritten. A theory feels intuitive because it matches our experience. Fireworks fade after bursting, coffee cools instead of reheating itself, and we remember yesterday but not tomorrow. But B theory argues this flow is a trick of perception, not reality. Einstein's relativity supports this with its block universe model, where observers moving at different speeds can't even agree on what now means. If the present isn't universal, how can it be fundamentally special? Here's where B theory gets radical. If all moments are equally real, then your fifth birthday isn't gone. It's still out there in the temporal landscape, just as real as the device in your hands right now. Death loses its usual meaning. From a four-dimensional perspective, you're always alive somewhere in the continuum. This doesn't mean time travel is possible. You can't rewrite history any more than you can edit a mountain's position on a map. Events are fixed in the grand structure, like frames in a film strip. But how does this explain our vivid sense of time moving? B theorists compare it to watching a train pass by. The cars seem to move, but really, you're just focusing on different parts of the static train. Consciousness might work similarly, creating the sensation of flow by highlighting successive nows in the eternal block. Some philosophers even suggest free will isn't threatened. Your choices are part of the block's geometry, like a novelist deciding a plot twist while holding the completed book. The debate between A and B theories isn't just academic. It shapes how we understand everything from quantum mechanics to the Big Bang. If B theory is correct, then entropy's arrow. The reason we see shattered cups but never spontaneously reassembling ones might be a local quirk of our corner of spacetime, not a cosmic rule. Distant regions could have reversed or even circular time arrows with no single flow governing the whole universe. Critics argue B theory feels sterile, stripping time of its dynamism. But its defenders counter that it's the ultimate democratization of existence. No moment is privileged over another. Your first kiss and your last breath are both eternal coordinates in the vast temporal atlas, not lost, not coming, but always there. Whether this comforts or unsettles you, one thing's clear. Time is far stranger than our brains evolved to perceive, and the truth may lie in dimensions we've yet to unravel. What if the Big Bang wasn't a beginning, but a rebirth, a cosmic reset triggered by a collision between entire universes? This is the spine-tingling premise of the ekpyrotic universe theory, a radical alternative to the standard Big Bang narrative. Instead of a fiery singularity birthing reality from nothing, this model paints a picture of endless cycles where our universe is just one chapter in an infinite saga of collisions between higher dimensional membranes or brains. Imagine two enormous sheets of spacetime floating in a hidden dimension like parallel pages in a book. These brains drift slowly toward each other, drawn by an unseen force. When they collide, the impact unleashes unimaginable energy, not as an explosion, but as a smooth, searing transformation that resets the cosmos. All the matter, energy, and even the fabric of time itself are stretched, scrambled, and reborn in the aftermath. The Big Bang, in this view, was just the latest collision in an endless dance. The name ekpyrotic comes from the ancient Greek word for conflagration, and it's fitting. But unlike the chaos of a wildfire, this process is precise. The model solves some of the Big Bang's biggest puzzles, like why the universe appears so uniform in all directions. In standard cosmology, this smoothness requires an unlikely cosmic inflation, a faster-than-light expansion in the first fractions of a second. The ekpyrotic model replaces inflation with the gentle, inevitable approach of the brains. Their near-perfect alignment before collision naturally explains the universe's uniformity, like two sheets of glass pressing together and leaving no wrinkles. Here's where it gets stranger. If time exists outside these brains in the higher dimensional bulk they float through, then each collision might not erase the past but fold it into the next cycle. Information, in some form, could persist across cosmic resets, like a story being rewritten with each iteration. Some versions of the theory even suggest that dark energy, the mysterious force accelerating our universe's expansion, is a shadow of the next impending collision, a cosmic countdown we're only beginning to sense. But how could brains, these unimaginably vast structures, exist without our noticing? String theory provides a possible answer. Just as a shadow is a two-dimensional projection of a three-dimensional object, our universe might be a three-dimensional slice of a higher dimensional reality. The brains could be all around us, mere fractions of a millimeter away in a direction we can't perceive. Their collisions wouldn't feel like crashes, but as the birth of time itself, resetting clocks across existence. Critics point out gaps in the theory, like the exact mechanism that separates brains after collision, or how quantum fluctuations imprint on the new universe. Yet the elegance of the ekpyrotic model is undeniable. It offers a vision of time not as a straight line with a beginning and end, but as a pulsing rhythm, an eternal heartbeat in the dark. Whether it's the true story of our cosmos remains unknown, but it challenges us to think bigger, to imagine time not as a single thread, but as a tapestry woven in dimensions beyond our sight. At the smallest scales of reality, where space and time crumble into a seething quantum foam, something bizarre happens to time itself. It vanishes, not like a clock winding down, but as if it never existed in the first place. This is the startling revelation of quantum gravity, where the familiar flow of seconds and minutes dissolves into a timeless void. The deeper we probe, the more time appears not as a fundamental feature of the universe, but as an illusion, a mirage conjured by processes we barely understand. Take the Planck scale, the universe's ultimate resolution, where distances shrink to 100 billionth of a trillionth of a trillionth of a centimeter. Here, spacetime isn't smooth and continuous. It's a churning froth of virtual particles flickering in and out of existence, where concepts like before and after lose all meaning. In this realm, quantum gravity suggests that time might not be a dimension at all, but something that emerges from the interactions of more basic elements. It's like watching a movie. The illusion of motion comes from static frames flashing by, but the frames themselves don't move. Similarly, time as we experience it could be a side effect of deeper, timeless physics. One compelling idea ties time's emergence to quantum entanglement, the spooky connection between particles that Einstein famously dismissed as action at a distance. When particles become entangled, their states are linked no matter how far apart they are. Change one, and the other instantly responds. Some physicists argue that this web of entanglement might weave the very fabric of time itself. Picture 1,000 metronomes ticking randomly in a room. At first, chaos, but as they subtly influence each other, rhythms emerge, patterns that weren't there before. Time, in this view, could be the collective beat of quantum entanglements synchronizing across the universe. The implications are staggering. If time emerges from entanglement, then the arrow of time, why we remember the past but not the future, might stem from how entanglement spreads. Early in the universe, particles were densely packed, their entanglements tightly knit. As space expanded, those connections stretched and diluted, creating a directionality that we perceive as time's flow. This could explain why entropy always increases, not because of some cosmic rule, but because the universe's quantum correlations are forever unraveling, like a sweater slowly coming undone. But what about the present moment, the now we all experience? If time is an illusion, why does it feel so vivid? Some theories propose that consciousness itself might be entangled with quantum processes, acting like a lens that focuses timeless reality into a linear stream. Think of a strobe light freezing a dancer's motion into snapshots. Our brains could be doing the same, stitching together timeless quantum states into the story we call time. This would mean free will isn't an illusion. It's our way of navigating a reality far richer than the clockwork universe we perceive. Critics argue that without time as a fundamental backdrop, physics loses its predictive power. Yet experiments with entangled particles keep blurring the lines. When measurements on one particle instantly affect its partner, could they be hinting at a realm where cause and effect aren't bound by temporal order? Some models even suggest that black holes, where time grinds to a halt at the singularity, might be windows into this timeless substrate. places where the universe's underlying code runs without a clock. The most radical take comes from physicist Carlo Rovelli, who imagines a world where time is entirely relational. Events don't happen in time, they define time by their relationships to each other. It's like asking, how tall is the Empire State Building? The answer depends on what you're comparing it to: another building, a person, a grain of sand. Similarly, when something happens might just be a question of what other events it's entangled with. In this view, the Big Bang wasn't the start of time, but the moment when the universe's events began weaving a web complex enough to give rise to the illusion of a timeline. Whether time is fundamental or emergent, one thing is clear: our experience of it is just the surface of something unfathomably deeper. The next time you check your watch, consider this: the seconds ticking away might be no more real than the flicker of a shadow on a cave wall, a fleeting glimpse of a reality where now is just one thread in a timeless tapestry. Ever had the eerie feeling that something about the world has changed, not subtly, but in ways that clash with your strongest memories? Maybe you vividly recall Nelson Mandela dying in prison in the 1980s, only to learn he was freed and became president. Or perhaps you swear the Berenstain Bears were once spelled Berenstein. These aren't just faulty recollections, they're examples of the Mandela effect, where thousands of people share identical false memories of events that never happened. But what if these glitches aren't just tricks of the mind? Could they be traces of something far stranger, evidence that we're brushing against hidden layers of time? At first glance, the Mandela effect seems like a quirk of psychology. Human memory is notoriously unreliable, prone to distortion and suggestion. But the sheer volume of people recalling the exact same incorrect details raises unsettling questions. Why do so many remember the Monopoly man wearing a monocle when he never did? Why do countless fans insist Darth Vader said, "Luke, I am your father," when the actual line is, "No, I am your father"? These aren't random misrememberings, they're startlingly specific, as if an entire population briefly accessed a timeline where things were different. Some theorists propose these glitches could be artifacts of temporal bleed, through moments where alternate versions of reality briefly overlap. Think of time not as a single thread, but as a woven fabric where strands occasionally cross. In one thread, the Berenstain Bears exist; in another, it's Berenstain. When these threads brush against each other, fragments might seep through, leaving groups of people with shared memories of events that never occurred in this timeline. This aligns with quantum interpretations, where every decision spawns branching universes, each with subtle variations. If consciousness somehow flickers between these branches, we might carry imprints of timelines we've almost but not quite inhabited. The implications grow even stranger when you consider quantum entanglement. Particles linked across space instantly mirror each other's states, defying classical limits. Could entangled timelines produce similar effects? If two versions of reality are quantum linked, a shift in one might ripple into the other, leaving residual memories like echoes in a canyon. This could explain why Mandela effects often cluster around cultural touchstones, movies, logos, historical events. These are moments where collective attention focuses, creating nodes where timelines might tangle or overlap. Critics argue these ideas stretch science beyond recognition, yet similar concepts appear in cutting-edge physics. The holographic principle suggests our three-dimensional reality might be a projection of information stored on a two-dimensional surface. If true, glitches in that data could manifest as inconsistencies in our shared past. Even string theory's hidden dimensions might allow for information leakage between parallel realities, where minor changes in one brain imprint on another. The most haunting possibility: if the Mandela effect reveals glimpses of alternate timelines, it undermines our trust in reality itself. What if facts we take for granted, the color of a stop sign, the lyrics to a song, are less solid than we think? Temporal glitches might be the universe's way of reminding us that time isn't a straight path, but a labyrinth with doors we've yet to open. Next time you hear someone insist it was definitely that way, consider this. Maybe in some corner of the multiverse it was. Every choice you make, from what you eat for breakfast to the career you pursue, sends ripples through reality. But what if those ripples don't just fade away? What if each one branches into entirely new universes, like a cosmic tree growing infinite limbs? This is the timescape multiverse theory, where time doesn't just flow, it sculpts, carving out endless variations of existence with every passing moment. Picture a vast, undulating landscape where every hill, valley, and river represents a different timeline, each one shaped by the decisions of countless versions of you. The idea starts with quantum mechanics, where particles exist in superpositions multiple states at once, until observed. The many worlds interpretation takes this further, suggesting that every quantum possibility spawns a new universe. But the timescape theory adds a breathtaking twist. These branching realities aren't just parallel lines, they're interconnected, influencing one another like threads in a grand tapestry. Imagine throwing a stone into a pond. In classic multiverse models, each splash creates a separate, isolated universe. But in the timescape, those splashes overlap, their waves mingling to create patterns no single timeline could produce alone. This could explain phenomena like déjà vu or intuitive hunches. Those moments of inexplicable familiarity might be glimpses of adjacent timelines brushing against our own, like whispers from realities where similar events unfolded. Think of it as cosmic déjà vu, not just remembering a moment, but sensing its echoes across the multiverse. Even creativity could stem from this cross-dimensional leakage, with artists and inventors tapping into ideas born in alternate versions of themselves. Critics argue that without observable evidence, the timescape multiverse remains speculative. But supporters point to quantum entanglement, where particles mirror each other's states instantly across vast distances. If particles can communicate faster than light, why not entire timelines? Some models even suggest dark energy, the mysterious force accelerating the universe's expansion, could be the gravitational pull of nearby brainworlds, their timelines warping ours in subtle ways. The most haunting implication: you might not be who you think you are. The you in this timeline could be a composite of choices made across countless others, your identity woven from threads of alternate lives. Every regret, every road not taken might still be playing out somewhere in the timescape, with versions of you living those unchosen paths. It's a humbling thought. The universe isn't just vast in space, but in time, and every decision you make sends new routes spiraling into the infinite. Picture a universe where time doesn't just flow forward, it spirals, loops, and even folds back on itself like a Möbius strip. This is the wild landscape of Lorentzian geometry, a mathematical framework where time behaves less like a straight arrow and more like a tangled thread. Named after Dutch physicist Hendrik Lorentz, this geometry underpins Einstein's relativity, but its implications stretch far beyond. If our universe follows Lorentzian rules, hidden dimensions of time could unlock phenomena straight out of science fiction wormholes, closed time-like curves, even passages to the past. At its core, Lorentzian geometry treats time and space as intertwined yet fundamentally different. Unlike Euclidean geometry, where distances are always positive, Lorentzian spacetime introduces a twist: time intervals can be negative. This isn't just a quirk of math, it's the reason high-speed travel slows clocks and why black holes warp time into a standstill. But here's the radical part: certain configurations in this geometry allow for paths where time circles back to its starting point. Imagine drawing a line on a piece of paper, only to curve it around until it meets itself. Now replace that line with a world line, the trajectory of an object through space-time. In Lorentzian universes, these loops aren't just possible, they're inevitable under the right conditions. One jaw-dropping example is the Tipler cylinder, a hypothetical object first proposed by physicist Frank Tipler. Picture a cylinder of near-infinite density spinning at relativistic speeds. According to Lorentzian math, the frame-dragging effect of this rotation would twist spacetime so severely that time itself coils into a loop. Travel around the cylinder in just the right way, and you'd return to your own past. Critics argue such structures would require exotic matter to avoid collapsing into a singularity, but the math holds, proving that Lorentzian geometry doesn't just permit time travel, it demands it under extreme circumstances. The real magic happens when you consider multiple temporal dimensions. If our familiar flow of time is just one axis in a Lorentzian framework, additional time dimensions could exist at right angles to it, like shadows cast by a higher dimensional clock. In this view, phenomena like quantum entanglement start making eerie sense. Two particles influencing each other instantly across light years might not be breaking causality. They could be communicating through hidden time channels, bypassing our linear experience entirely. Some models even suggest that dark energy's mysterious acceleration of the universe could stem from these extratemporal dimensions exerting pressure on spacetime's expansion. The implications are staggering. A Lorentzian universe might harbor regions where time flows backward, sideways, or in fractal patterns beyond human perception. Civilizations in such zones could experience reality in ways we can't fathom, remembering the future, aging in reverse, or perceiving cause and effect as a tangled web rather than a sequence. Even consciousness itself might be bound to our single-time perspective, leaving entire realms of experience locked away. Yet the most haunting question remains: if Lorentzian geometry allows these wonders, why don't we see them? The answer could lie in scale. Just as a flatlander can't perceive the third dimension, our biology and instruments might be blind to time's full architecture. Wormholes could lurk in every atom, time loops in every black hole, all invisible until we learn to decode the deeper math of existence. One thing's certain: if the universe is Lorentzian at its core, then time isn't just a river carrying us forward. It's an ocean with currents, whirlpools, and depths we've only begun to explore. We like to believe the present moment is special, that the past is gone, the future's not yet here, and only now is real. This intuitive view, called presentism, treats time as a fleeting spotlight moving from one instant to the next, but relativity shatters this comforting idea. Einstein showed that now isn't universal. What's present for you might already be past for someone moving at high speed, or future for someone near a black hole. If the present can't even be agreed upon, how can it be the only thing that exists? Enter Eternalism, the radical alternative. Instead of a single now sliding forward, Eternalism treats time like space, a vast, unchanging block where every moment, from the Big Bang to the heat death of the universe, exists simultaneously. Think of a DVD. The whole movie is there, but your consciousness is the laser reading one frame at a time. In this view, your birth, your first heartbreak, and events centuries from now are equally real, just located at different temporal coordinates. The debate gets fierce when you apply quantum mechanics. Presentists argue that quantum uncertainty proves the future is truly open. Particles don't have definite states until measured, suggesting reality is built moment by moment. But Eternalists counter that quantum superpositions might just be our limited view of a higher dimensional tapestry. Imagine flipping through a choose-your-own-adventure book where every possible path already exists. Your choices feel real, but the branches were always part of the whole. Here's where relativity delivers the knockout punch. If two astronauts pass each other at near light speed, their clocks desynchronize. Each genuinely experiences different sequences of events as present. There's no privileged frame of reference to say who's really correct. This forces a chilling conclusion. If presentism were true, reality itself would fracture into conflicting versions, each insisting its now is the genuine one. Eternalism avoids this by treating all perspectives as equally valid slices of the timeless block. Yet presentism refuses to die. Some philosophers propose that consciousness itself might collapse time into a flowing present, like a projector illuminating one film frame at a time. Others argue physics can't explain the vividness of now. Why does this moment feel alive if the past and future are equally real? The tension between these views exposes a deep rift in how we understand existence. Is time something we're inside, or is it something we're made of? The answer might lie beyond both. Some quantum gravity models suggest time emerges from more fundamental processes, like temperature arising from molecular motion. In this view, presentism and eternalism could both be illusions, two sides of a coin we've yet to flip. Until then, the debate rages on, leaving us with a haunting thought. If even time isn't what it seems, what else might we be getting wrong? Quantum entanglement already bends the rules of space, but what if it bends time too? The time entanglement hypothesis takes this mind-bending phenomenon and flips it sideways, proposing that particles can be linked not just across distances but across moments. Imagine two electrons entangled so deeply that measuring one today instantly determines the state of the other, not just somewhere else in the universe but in the past. This isn't just spooky action at a distance, it's spooky action across time itself. The idea builds on quantum mechanics' weirdest quirk. When particles entangle, they share a single quantum state, no matter how far apart they are. Change one and the other changes instantly, defying Einstein's speed of light limit. But if entanglement ignores space, why should time be any different? Experiments like the delayed choice quantum eraser hint at this possibility. In these tests, decisions made after a particle is measured seem to retroactively alter its earlier behavior. It's as if the particle knows what choice will be made in the future and adjusts its past accordingly. Retrocausality, the idea that effects can precede causes, sounds like pure science fiction. Yet mathematically, the equations work just as well backward as forward. Some interpretations suggest that quantum probabilities aren't fixed until observed, meaning future measurements could ripple backward to shape past events. Picture a sculptor working on a block of marble. From the marble's perspective, the final statue seems to emerge organically, but in reality, every chip is guided by the sculptor's future intent. Similarly, entangled particles might negotiate their states across time, with future observations carving reality from quantum potential. Critics argue this violates causality, creating paradoxes like a detector influencing a particle's state before it's even built. But proponents counter that retrocausality doesn't mean changing the past, just that the past and future are codependent, like two ends of a tug-of-war rope. The universe might resolve these loops self-consistently, ensuring no true contradictions arise. Think of it like a detective novel where the ending subtly rewrites earlier clues. The story stays coherent, but your understanding of the beginning shifts. The implications are staggering. If entanglement weaves through time, it could explain phenomena like precognitive dreams or déjà vu, fleeting moments where future and past momentarily sync. It might even unlock new forms of communication, where messages are encoded in particles whose states were determined after they were sent. One thing's certain: if time entanglement holds, the universe isn't just connected across space, but across epochs, with every moment subtly whispering to every other. The past, present, and future might be far more tangled than we ever imagined. Imagine a universe that lasts forever, not just billions or trillions of years, but an eternity where time stretches forward without end. In such a cosmos, even the most improbable events become inevitable given enough time. Now picture this: a fully formed, self-aware brain suddenly popping into existence, complete with fabricated memories and senses, convinced it's a real person living in a real world. This isn't the plot of a dystopian sci-fi novel. It's the Boltzmann brain paradox, a thought experiment so unsettling that it challenges everything we assume about time, memory, and even reality itself. The paradox gets its name from physicist Ludwig Boltzmann, who suggested that entropy, the universe's tendency toward disorder, could occasionally reverse in small pockets through random fluctuations. Given infinite time, these fluctuations could produce anything, no matter how unlikely. A single hydrogen atom arranging itself into a strawberry, given enough years, it's certain. An exact duplicate of Earth with your doppelganger drinking coffee right now, statistically guaranteed. But the ultimate freak accident would be a fully conscious brain materializing out of chaos, complete with the illusion of a past. In an eternal universe, Boltzmann brains should outnumber ordinary, biologically evolved minds by an unimaginable margin, so why aren't we one of them? Here's where time's structure gets turned inside out. If Boltzmann brains are possible, then the present moment you're experiencing right now could just be a fleeting fluctuation, a brief spark of order in an otherwise lifeless void. Your memories of childhood, your sense of identity, even the device you're holding might not be real, but temporary hallucinations of a brain that formed seconds ago. The paradox forces us to confront a terrifying question. How do we know we're not Boltzmann brains ourselves? Critics argue this scenario is absurd. The energy required to spontaneously create a functioning brain is so astronomically high that even eternity might not suffice. But supporters fire back with an even stranger idea. Quantum mechanics allows for virtual particles to pop in and out of existence all the time. If space itself can briefly conjure particles from nothing, why not entire minds? Some cosmologists propose that the paradox could be resolved if our universe isn't eternal after all. If time had a definite beginning like the Big Bang and will have an end, cutting off the infinite window needed for Boltzmann brains to dominate. Yet the deepest implication isn't about brains at all, it's about time's arrow. The paradox suggests that in an eternal universe, the distinction between past, present, and future might be meaningless. If a brain can materialize with artificial memories of a past that never happened, then time's linearity could be an illusion, a local quirk of our corner of reality. In the grand scheme, time might not flow so much as stutter, with consciousness flickering in and out of existence like lightning in a dark sky. The Boltzmann brain paradox doesn't just bend the rules of physics, it shatters our trust in experience itself. Next time you recall a childhood memory or plan for tomorrow, consider this. The universe might be old enough to have conjured you and everything you know into being just a moment ago. Whether a thought experiment or a profound truth, one thing's certain: reality is far stranger than it seems. At the smallest scales of existence, where gravity and quantum mechanics collide, our intuitive sense of causality might completely unravel. This is the mind-bending world of time loop quantum gravity, a theory suggesting that the fabric of spacetime could twist into microscopic loops where cause and effect dance in circles. Instead of the rigid, one-way street of classical physics, time at the quantum gravity level could resemble a Möbius strip, where beginnings and endings blur into an endless knot. Consider how gravity warps time on cosmic scales. Black holes slow it to a crawl, and the Big Bang stretches it beyond recognition. Now shrink that phenomenon down to the Planck scale, where spacetime itself becomes a seething quantum foam. Here, the equations of loop quantum gravity, a leading approach to unifying relativity and quantum mechanics, predict that time might not flow smoothly but stutter in tiny, discrete steps. In this pixelated landscape, temporary closed time-like curves could flicker in and out of existence like bubbles in boiling water. These microscopic time loops wouldn't last long enough for a person to revisit their childhood, but they might allow particles to briefly interact with their own past states, creating feedback loops that defy classical logic. Imagine a single electron caught in one of these loops. It moves forward in time, interacts with an earlier version of itself, and that interaction changes its initial state, a paradox that would make Newton's head spin. Yet quantum mechanics already embraces such weirdness. The famous double-slit experiment shows particles behaving as if they've explored multiple paths before choosing one. Time loop quantum gravity takes this further, suggesting particles don't just sample alternate routes in space, but in time as well. It's as if the universe allows for provisional paradoxes at the quantum scale, smoothing them out before they escalate to macroscopic absurdity. This idea gains traction when you examine quantum entanglement. Two particles can instantaneously influence each other across vast distances, seemingly communicating faster than light. But if space-time at their scale contains hidden time loops, their spooky action might just be routing signals through microscopic shortcuts in causality. Think of it like a pair of ants on a crumpled piece of paper. What looks like action at a distance could just be them stepping through a fold in the paper's surface, hidden from our three-dimensional perspective. Critics argue that even microscopic time loops could destabilize reality, allowing information to multiply endlessly like a hall of mirrors. Yet proponents point to the Novikov self-consistency principle, which suggests the universe might enforce logical consistency, editing out any loops that create true paradoxes. In this view, time loops wouldn't rewrite history but constrain it, like a river carving its own banks, every twist and turn already accounted for in the grand equation. The implications are staggering. If time loops exist at quantum scales, they could explain why particles seem to remember their paths in experiments like the quantum eraser. Dark matter's elusive behavior might even trace back to particles hopping through hidden temporal circuits we can't directly observe, most tantalizing of all. These loops could be the universe's way of testing causality itself, probing the boundaries between past and future in ways we're only beginning to glimpse. So the next time you check your watch, remember, those ticking seconds might be the smoothed-out average of a far wilder reality where time doesn't just march forward, it spirals, stutters, and occasionally ties itself into knots too small for us to see. The Big Bang wasn't the calm beginning we often imagine. It was a violent, exponential expansion, a cosmic inflation that stretched space-time like taffy in a fraction of a second. But what if that explosion didn't just birth our universe? What if it seeded a vast, bubbling multiverse where time itself behaves differently in each pocket of reality? This is the temporal landscape of inflation, a theory that suggests the early universe's rapid expansion didn't just create space, it sculpted time into countless variations, each with its own rules, rhythms, and even arrows of entropy. Picture a boiling pot of water with bubbles forming and popping at random. Each bubble represents a newborn universe, and the foam between them is the inflationary field, a seething energy that drives eternal expansion. In some bubbles, time might flow forward as we know it, with entropy increasing and cause preceding effect. In others, time could run backward, with shattered teacups leaping back into their owner's hands and stars assembling from scattered stardust. Still others might have no arrow of time at all, existing in a state of perfect symmetry where past and future are indistinguishable. This idea stems from string theory's landscape concept, where the laws of physics, including time's behavior, are determined by how higher dimensional fields settle into stable configurations. Just as water freezes into different crystal structures depending on temperature and pressure, the inflationary field could have frozen into countless variations, each birthing universes with unique temporal properties. Some might even host multiple time dimensions where causality isn't linear but branches like a tree or loops like a Möbius strip. The implications are staggering. If time's arrow isn't universal but local, it could explain why our universe seems so finely tuned for complexity. In most inflationary bubbles, time might be too chaotic or too static for life to emerge. But in rare pockets like ours, where entropy increases steadily, consciousness gets a chance to unfold. This would make our experience of time not a cosmic default, but a lottery win, a fleeting alignment of conditions that lets us perceive change at all. Critics argue this theory is untestable, a philosophical escape hatch rather than hard science. Yet subtle clues might lurk in the cosmic microwave background, the afterglow of the Big Bang. Strange anomalies in its polarization patterns could hint at collisions with other bubbles in the multiverse, each carrying echoes of alternate temporal laws. Even dark energy's mysterious acceleration might be a shadow of nearby universes where time runs backward, their gravitational pull warping our expansion in ways we're only beginning to model. The most haunting possibility: if the temporal landscape is real, there could be universes where time isn't just reversed, it's fractured, with chunks of history repeating like a broken record, or dimensions where cause and effect are shuffled like a deck of cards. In such realms, logic itself might be alien, with civilizations reasoning in ways we can't fathom, their memories and prophecies intertwined in knots no human mind could untangle. So the next time you check your watch, consider this: those ticking seconds might not be a universal constant, but a quirk of cosmic geography, a fleeting rhythm in a symphony where time itself has infinite variations. Whether a profound truth or a beautiful speculation, one thing's certain: the universe is far stranger than the clocks on our walls would ever suggest. What if time doesn't flow like a river but clicks forward like the hands of a cosmic clock? Digital physics proposes a radical idea: that the universe isn't just governed by equations, but is fundamentally computational, running on a substrate of tiny, discrete operations. In this view, time might not be continuous at all, but a series of finite steps like frames in a movie or pixels on a screen, each one processing a sliver of reality before flipping to the next. The smooth passage of seconds we experience could be an illusion, the result of trillions of microscopic ticks happening far too quickly for us to perceive. Think of the universe as the ultimate quantum computer. Just as your laptop processes information in bits, reality might compute itself in Planck-scale units, chunks of time so small that a single second contains more of them than there have been seconds since the Big Bang. At this level, events wouldn't unfold seamlessly but incrementally, like a flipbook animation where each page is a complete snapshot of existence. This could explain why quantum mechanics deals in probabilities and sudden jumps. Particles aren't moving through smooth space, but rendering frame by frame, with hidden calculations determining their positions between ticks. The implications are staggering. If time is discrete, there might be layers of processing we're blind to, subroutines running beneath the surface of reality, executing the code that generates gravity, electromagnetism, even consciousness itself. Some theories suggest these hidden operations could account for dark energy's mysterious effects, like glitches in the cosmic program causing space-time to expand faster than expected. Others propose that black holes might be nature's garbage collectors, regions where information gets compressed and recycled to free up memory in the universal mainframe. This isn't just metaphorical. Certain quantum gravity models, like loop quantum gravity, explicitly describe space-time as granular, with time emerging from the interactions of these tiny, indivisible pieces. Even the speed of light could reflect the universe's processing limit, a cosmic clock speed ensuring no computation outruns the system's ability to update. It's as if reality has a refresh rate and we're only perceiving the output, not the circuitry humming beneath. But here's the real twist: if the universe is computational, who or what is running the program? Some theorists argue it could be self-simulating, a closed loop where the laws of physics bootstrap their own existence. Others entertain the possibility of nested realities, where our universe is a simulation inside a higher dimensional computer, with time's ticks synchronized to an external processor we'll never see. The most haunting possibility: that the program has bugs, glitches in discrete time might manifest as statistical anomalies in particle physics, or even déjà vu moments when the universe briefly stutters between frames. Yet the most profound takeaway isn't about aliens or simulations. It's about time's nature. If reality computes itself step by step, then free will might not be an illusion but a feature. Our choices could be the universe's way of resolving quantum probabilities, like a program waiting for user input before rendering the next scene. The past would be stored data, the future a buffer of possible states, and the present, the only moment we ever experience, the instantaneous output of an unimaginably vast calculation. Whether this vision is poetry or physics, one thing's certain: the ticking of your watch might be far stranger than you ever imagined. One moment you're walking down a familiar street. The next, the pavement beneath your feet feels different, the air smells like coal smoke, and strangers in outdated clothing stare at you as if you're the anomaly. These are time slips, surreal episodes where people report suddenly finding themselves in another era, only to snap back to the present seconds or minutes later, disoriented but utterly convinced of what they experienced. Unlike dreams or hallucinations, time slips often involve multiple witnesses and inexplicable physical details: cobblestones where asphalt should be, vintage cars with license plates matching historical records, even conversations in long-dead dialects. So what's really happening? Could these be fleeting breaches in time's fabric, or glimpses into dimensions where history plays on loop? Take the infamous case of two English women visiting Versailles in 1901. While touring the Petit Trianon, they insisted they'd wandered into the late 1700s, encountering figures dressed in pre-revolutionary attire, including a woman sketching who matched descriptions of Marie Antoinette. No amount of historical debunking could shake their certainty. Similar accounts pepper modern times: a Tokyo businessman stepping into a 1920s-era alleyway that vanished upon exit, or a couple in 1979, Liverpool, claiming they drove through a tunnel only to emerge in a 1950s-style traffic circle before it dissolved around them. Skeptics dismiss these as memory glitches or elaborate confabulations, but the sheer specificity and emotional resonance of these events leaves even scientists intrigued. One compelling explanation ties time slips to quantum mechanics. Under certain conditions, particles can tunnel through barriers that should be impenetrable. If spacetime itself has a quantum foam-like structure at microscopic scales, could rare fluctuations create temporary tunnels linking different eras? Think of it like a cosmic short circuit, a brief overlap between timelines that normally run parallel. This aligns with string theory's brainworld models, where our universe is a three-dimensional membrane floating near others in higher dimensional space. A local warp in the brain might momentarily fuse 2 points in time, allowing slippage before snapping back like a rubber band. Then there's the psychological angle. Human brains are prediction machines, constantly constructing our sense of now by stitching together sensory input with memory. Neurological quirks like temporal lobe epilepsy or dopamine surges can distort this process, creating hyper-realistic false memories. But this fails to explain cases where multiple unrelated witnesses share identical details, or when physical traces like sudden temperature drops or period-accurate sounds accompany the event. The most radical theory: time slips might be localized collapses of the wave function, moments when quantum probabilities briefly resolve into a different past or future than the one we collectively experience. Imagine reality as a sheet of paper crumpled into a ball. Most of the time we perceive it as smooth, but occasionally folds bring distant points into contact. If consciousness itself is entangled with quantum states, as some interpretations suggest, certain minds might tunnel into these folds, experiencing alternate timelines before decoherence snaps them back. Whether glitches in reality's code or neural oddities, time slips force us to confront a tantalizing possibility. The walls between past, present, and future might be thinner and weirder than we ever dared assume. The next time you turn a corner and feel the air shift, ask yourself, are you stepping into another place or another time? What if the expansion of our universe isn't just happening within time, but because time itself is changing? the time boundary universe theory suggests a radical idea that our cosmos isn't merely drifting apart in space, but approaching an invisible frontier where the very nature of time transforms. Picture a river flowing toward a waterfall. The water speeds up as it nears the edge, not because it's being pushed, but because the ground beneath it is collapsing. Similarly, dark energy's mysterious acceleration of the universe might not be a force at all, but a symptom of time's hidden architecture buckling at its outer limits. This concept flips conventional cosmology on its head. For decades, scientists assumed dark energy was some form of exotic matter or energy causing space to expand faster. But what if the culprit isn't in the universe, it's the universe's relationship to time? Imagine living inside a balloon that's not just inflating, but where the rubber itself is thinning near the edges. As galaxies approach this time boundary, their clocks could tick differently, their light stretching into unrecognizable frequencies as the dimensionality of time shifts around them. The redshift we interpret as cosmic acceleration might actually be a distortion effect, like a ship's horn dropping in pitch as it sails away. Only in this case, the horn itself is changing as it moves through time's evolving landscape. Evidence for this theory could lie in the cosmic microwave background, the afterglow of the Big Bang. Tiny anomalies in its polarization patterns might reveal areas where time's flow subtly warps like currents in an invisible ocean. Even more tantalizing are supernova observations. Certain distant explosions appear dimmer than expected, as if their light is battling against a fundamental change in time's rules as it travels to us. Proponents argue this could explain why dark energy's effects seem to strengthen as the universe ages. We're not seeing a force gaining power, but a boundary drawing nearer. Critics counter that the math remains speculative, with no clear mechanism for how time could transition at cosmic scales. Yet similar ideas appear in string theory, where higher dimensional brains can collide or stretch, altering the laws of physics in their wake. If our universe is a four-dimensional membrane floating in a higher dimensional bulk, then time's behavior at our boundary might resemble a coastline eroding into an unseen sea, each wave carrying fragments of our familiar chronology into something stranger. The most haunting implication: if time's dimensionality shifts at the edge of the cosmos, there might be regions where causality unravels entirely, zones where effect precedes cause, or where events loop like broken records. Civilizations born near these frontiers could perceive reality in ways we'd find incomprehensible, their histories written in reverse or branching like fractal trees. For them, the Big Bang might not be a distant memory, but a destination looming ahead, as inevitable as the waterfall is to the river. Whether a profound truth or a beautiful mathematical fiction, the time boundary universe forces us to confront a humbling possibility. That dark energy isn't pulling the universe apart, but time itself is turning inside out, rewriting its own rules as the cosmic story unfolds. The deeper we look, the more time reveals itself not as a stage, but as a player, one whose final act might be stranger than anything we've dared imagine. What if time isn't woven into the fabric of the universe, but spun from the threads of our own awareness? The idea that consciousness creates time turns everything we assume about reality inside out. Instead of time being an external river carrying us forward, this theory suggests it's more like a projector beam from our minds illuminating moments into existence simply by observing them. In this view, the past isn't a fixed record and the future isn't unwritten. Both are fluid, shaped by the act of perception itself, with hidden dimensions unfolding like layers of a dream we're all collectively dreaming. Think of a film reel lying in the dark. The images exist, but they don't form a story until light passes through them. Similarly, consciousness could be the light that animates static moments into a flowing narrative we call time. Quantum mechanics already hints at this with the observer effect, where particles behave differently when measured, as if aware they're being watched. If microscopic reality responds to observation, could the same be true for time's structure? Some interpretations suggest that the famous Schrödinger's cat isn't just alive and dead until observed. It exists in all possible states across a spectrum of untapped temporal dimensions, collapsing into a single timeline only when consciousness interacts with it. This idea finds eerie parallels in ancient philosophies. Hindu texts describe time as Maya, an illusion crafted by the mind. Indigenous cultures often view time as cyclical, with past and future coexisting in a sacred present. Even modern neuroscience reveals that our brains don't process the world in real time. There's a slight delay as sensory data gets woven into a coherent story. What we experience as now is actually a reconstructed simulation, a best guess our minds assemble microseconds after events occur. If our perception of time is already a construct, how much further might the rabbit hole go? The implications are staggering. If consciousness generates time, then phenomena like precognition or déjà vu might not be glitches. They could be moments when the mind brushes against its own scaffolding, glimpsing the raw framework beneath the illusion. Near-death experiences where people report lifetimes flashing before their eyes could be the brain unraveling its temporal weaving, revealing the timeless void beneath. Even memory takes on new meaning, not as a record of the past, but as an active reconstruction, a story we tell ourselves to maintain the fiction of continuity. Critics argue this veers into solipsism, reducing reality to a collective hallucination. Yet supporters counter with hard physics. The Wheeler-DeWitt equation, a cornerstone of quantum gravity, famously lacks a time variable, suggesting the universe at its deepest level might be timeless, with change emerging only at higher levels of complexity. If time isn't fundamental, where does it come from? Consciousness could be the missing link, the process that transforms a frozen quantum landscape into the dynamic world we inhabit. The most radical experiments testing this theory involve altered states of awareness. Psychedelics, meditation, and sensory deprivation can dramatically distort time perception. Minutes stretch into eternities, sequences jumble, and some report touching a dimensionless eternal now. These experiences might be more than chemical quirks. They could be glimpses of consciousness operating without its usual temporal filters, revealing the mind's role in stitching reality together. If hidden dimensions of time are mental constructs, then parallel universes might not be out there in space, but nested within layers of awareness. Your dreams, for instance, could be alternate timelines flickering in the unused corridors of perception. This reframes time travel as an introspective journey exploring forgotten memories, might literally be revisiting past dimensions of yourself, while envisioning the future could be tapping into probabilities not yet solidified. The haunting question remains, if consciousness creates time, what happens when it stops? Death might not be an end, but a return to the timeless substrate, a dissolution of the projector beam, leaving only the untouched reel of uncollapsed possibilities. Whether science or metaphysics, one thing's certain: the closer we look at time, the more it dissolves into the very act of looking, leaving us to wonder, are we passengers in time or its architects? Every moment you've experienced, every heartbeat, every sunset, every breath feels like an unshakable truth, an irrefutable point along time's arrow. But what if that arrow isn't flying through empty space? What if it's riding the crest of something far vaster, an unseen current in a higher dimensional ocean where time itself evolves, mutates, and grows? This is the meta-time hypothesis, a theory so dizzying it suggests our entire experience of past, present, and future might just be a single frame in a film that's still being developed. Imagine standing on a train, watching the landscape blur past. You perceive movement, but only because the tracks beneath you exist. Now picture those tracks as meta-time, an invisible dimension where the rules of time aren't fixed but fluid. In this view, the flow we experience isn't fundamental. It's a shadow cast by deeper shifts in time's own structure. Just as space expanded after the Big Bang, time itself might be undergoing its own cosmic evolution, with early epochs operating under different temporal laws than we know today. The seconds ticking on your watch, those could be the current settings in a universe still figuring itself out. This idea isn't pure philosophy, it emerges from the edges of quantum gravity research. When physicists attempt to unify general relativity with quantum mechanics, they often hit a paradox. Time seems to vanish from the equations at the smallest scales. One radical explanation is that time isn't disappearing, it's being reset by processes in meta-time, like a canvas being repainted by an unseen hand. Some models even suggest that entropy's irreversible march could be a symptom of meta-time's directionality, a higher dimensional arrow we're embedded within without realizing it. Think of it like a tree growing rings. Each ring represents an era where time's structure morphs slightly, maybe causality loops more tightly in one epoch or flows backward in another. We're confined to a single ring, perceiving its grain as the only possible way time could work. But outside our slice, in the meta-time beyond, other rings exist with entirely different rules. Civilizations arising in those layers might experience reality in ways we can't fathom, beings who remember the future, or for whom cause and effect are as malleable as clay. The most startling implication: if meta-time governs our temporal dimension, then the laws of physics might not be eternal truths but local ordinances. Constants like the speed of light or the strength of gravity could be time-tuned, subtly shifting as meta-time progresses. This could explain mysteries like dark energy. What if the universe's accelerating expansion isn't due to some hidden force, but because time's own fabric is stretching differently in the meta-layer? Even the Big Bang might not have been a true beginning, but a transition point where time's previous structure collapsed and rebooted under new rules. Critics argue this borders on metaphysics. How could we ever test a dimension beyond time? Yet supporters point to anomalies in the cosmic microwave background, the afterglow of the Big Bang. Strange patterns in its temperature fluctuations might encode hints of a pre-Big Bang era, a meta-temporal relic bleeding through. Others suggest that quantum entanglement's instant connections could be threads trailing into meta-time, linking particles across what we perceive as separate moments. The deepest question of all: if time evolves, does consciousness evolve with it? Our brains might be wired to perceive time's current version, blind to its fuller geometry. Near-death experiences, psychedelic states, or even dreams could be fleeting moments when the mind brushes against meta-time's edges, glimpsing realities where time isn't linear, but layered, spiraled, or woven in ways we're only beginning to imagine. Whether a groundbreaking truth or a beautiful speculation, the meta-time hypothesis forces us to confront the humbling possibility that time as we know it isn't the stage, it's the performance. And somewhere beyond the curtains, in dimensions we can't yet see, the script is still being written. From time crystals that tick forever without energy to parallel universes where every choice spawns a new reality, we've explored theories that bend the very fabric of existence. We've peeled back layers of time like an infinite onion, each revealing dimensions where the past rewrites itself. Consciousness stitches together the present, and the future might already be set in stone. Some ideas, like the Boltzmann brain paradox, suggest our entire lives could be fleeting hallucinations of a mind that blinked into existence seconds ago. Others, like the Janus Point universe, paint time as a two-way mirror with another cosmos flowing backward on the far side. And let's not forget the timescape multiverse, where your alternate selves aren't just living different lives, they're experiencing time at rhythms you can't fathom, from eons unfolding in a blink to moments stretched into eternities. But here's the real kicker: these aren't just thought experiments, they're glimpses into what might actually be lurking beyond the limits of our perception. The universe doesn't owe us intuitive rules. Reality could be stranger than 1,000 sci-fi novels stacked together, and we're only deciphering the first page. So tell us, which theory rewired your brain? Was it the holographic universe where time is just a projection, or the meta-time hypothesis where even time itself evolves? Drop your mind-blown reactions in the comments, and if you're hungry for more cosmic mysteries, hit subscribe. Because trust us, this rabbit hole goes deeper than we could ever cover in one video. The universe is waiting to mess with your head all over again.